Okay, we will go ahead and finish up the substitution elimination material having to do with our alcohol functional group. It's worth noting that we aren't really going to talk about it in this section. For the amines, we're really primarily concerned about nomenclature and then the basicity. So those are going to be two homework things that you should probably focus on within chapter 10. Beyond that, I wouldn't stress too much about the material there because we aren't going to spend a whole lot of time on it. Okay, so let's go ahead and move on. So where we ended lecture on Wednesday was taking a look at some of the substitution reactions, kind of bulk of our alcohols, and we had already talked about our alcohols needing a some kind of activation. So in this case we're doing an acid-base activation, and in this case the alcohol acts as a base, and that generates, I don't know how many carbons there were, a really good leaving group. So one of our primary concerns is that we have this good leaving group. Now we could have a nucleophile come in and do a backside attack. Okay, so we've seen that already. That one was fairly standard, and probably going to be one of the more common versions of reactivity, particularly for substitution, that you'll see for alcohols. One of the more interesting substitution reactions would be using the species known as thionyl chloride, which is this next one. This is thionyl chloride. It's kind of fun because if you have a stereocenter, it maintains the stereochemistry of your starting material. Whereas in the case of our first substitution reaction up here, we end up losing, quote unquote losing the stereochemistry or stereocenter if we went through kind of an SN1 condition, so we're looking at larger substrates. If we went under SN2, we'd get inverted stereochemistry, okay, for our SN2. So it's kind of neat that in thionyl chloride we actually maintain, okay, so that's kind of fun, or something new about our thionyl chloride. And even with that, it works by still activating the alcohol into a good leaving group. So one of the intermediates we showed was that attacking and having this larger substrate structure. We now have a really good leaving group, and that's what allows for the substitution. Okay, so regardless of the type of reaction that we're going to do with our alcohols, almost all of them require some activation to get the alcohol to the point where it can react well enough. Because while it is polar, and it does generate a partial negative charge on the oxygen and a partial positive charge on our carbon and hydrogen, it's not quite enough to really push our chemistry beyond. Okay. The last reaction that I didn't quite get to as far as our substitution goes is actually now having our alcohol act as an acid. Okay, so what's going to happen here is we'll take a strong base, so we'll go kind of generically first. We'll just say our base is the one with electrons. The base comes in, takes the electrons, or shares electrons with hydrogen. Our electrons push onto that oxygen, and the intermediate we generate looks like this. Okay, and now we have a negative charge. That species is now a really good nucleophile, as well as a strong base. So if we bring in a partially positive carbon, say through an alkyl halide, we can get a substitution reaction. Okay, and that's what's happening in this next case. And we end up here with a new functional group, which we haven't really talked a whole lot about. We get an ether. Okay, so ethers can be fun because we minimize the reactivity that we would have seen from the alcohol, because these carbons kind of block the reactivity that we could see from the lone pair on that oxygen. So ethers are typically very, very unreactive for that reason. Okay. So I said we're going to look at this kind of generically first. So that's what we just did. And you'll notice that instead of our standard strong base, like sodium hydroxide, for instance NaOH, we're not using NaOH, we're using NaH. Okay? So it's a slightly different base than we've seen before, and that's because the alcohol, while it is acidic, is not really acidic enough to react with our hydroxide. So we have to use a stronger base. So we'll move up to something like sodium hydride. Okay, and so what we're going to go ahead and do now is take a look at some of those stronger bases and what we could potentially do with them. Okay, well, first we'll address why we do this. Okay, so if we want the alcohol to act as a nucleophile in a reaction, it has to have donatable electrons. So in our standard alcoholic state, we do have nucleophilic electrons, and so those could react as a nucleophile, but they aren't. It's not the greatest nucleophile. So what we could move to next, as a big red flag, is having a negative charge. Okay, so what we're going to try and do is somehow get that oxygen to be negative. To do that, we have to break one of the bonds near it. Okay, either the carbon or the hydrogen bond. The easier one to break will be the one with hydrogen, and we can do that using a base. Okay, the base with its electrons can come in, react with the hydrogen, and put the electrons on the oxygen, and we end up with that negatively charged species. So at that point we now have a much better nucleophile because of that negative charge, and it'll help us react further on down the road. Okay, so it's kind of a nice thing to do. And that's what we just had on the last slide. Okay, looking at adding a strong base, reacting with the alcohol first. So I think this is new for you guys, seeing these steps 1 and 2. So the first step of this reaction is to add our strong base. So the result of step 1 is producing the negatively charged oxygen. The result of step 2 gives us the final product. Okay, so we would have to specify these as individual steps because we're trying to separate these reagents away from each other. So they're individual steps along the way. If we mix it all at once, we could get other side reactions. So these steps 1 and 2 are just a way to condense what could be drawn out reactions into one simple, more approachable interaction or drawing. Okay. So what is going on with that sodium hydride? And I've noticed I've been making a lot of mistakes here with this. This is alcohols acting as acids to become nucleophiles. Okay, so why do we not use, say, sodium hydroxide? So we've given 2 reactions here. One with an alcohol and hydroxide. The easiest source of hydroxide would be NaOH. Okay, to produce our nucleophilic oxygen, okay, and water. Or we go through and we react, instead of sodium hydroxide, we react sodium hydride. You'll notice this is hydride now, not hydrogen ion. Okay, why is it hydride? Well, which is more electronegative, hydrogen or sodium? It may take a little while to kind of evaluate that one. Sodium's a metal, hydrogen's a nonmetal. Most nonmetals have higher electronegativities. We would expect these electrons to sit on the hydrogen, not on the sodium, which would mean I get H minus, okay, with that lone pair, and Na plus. Hydrogen ion is reserved for H plus. Since we're looking at H minus, hydride. Okay, that's where that name difference comes in. So sodium hydride reacts in a very similar reaction as we would expect with the hydroxide. Okay, so we can draw in our arrows. Sorry, let me do those in a different color so they stand out a little bit. So our electrons from our hydroxide come in, pull off the hydrogen from our alcohol. If we take a look at hydride, does pretty much the same thing. And if we take a look at our answers, we get virtually the same answers with both of these. Okay? And in fact, if we evaluate the stability of the other pieces, we would say both of these are relatively stable. We get water and we get hydrogen gas. Both are pretty darn stable. Okay, so it seems a bit odd. Why not use just sodium hydroxide? Okay, so to answer that, first thing we could do is evaluate what other information is given in these reactions. Okay, and that might be a little bit harder for you to see, but what is the difference between these? Let me go ahead and erase everything. Almost everything. I want that acid thing back up there. Okay, so when you look at these reactions, is there anything else that stands out as different? Okay, well, how about the arrow in between? Okay, in the case of the hydroxide, you'll notice I'm using a double-headed arrow, or sorry, two arrows. For those of you that took second semester general chemistry might remember this as an equilibrium arrow. Okay, and we've talked about it briefly this semester, but not a whole lot. What that arrow means is the reaction goes backwards and forwards. Okay, so if we tried to evaluate which side of the reaction was more stable, we could go through and look for the most reactive thing on each side. So we should, or you should, hopefully realize that the hydroxide is the most reactive on the reactant side, and our ethoxide is the most reactive on the product side. And we could evaluate the charges on each side. Well, the charge is held on the same type of atom in each case, with really no difference between them, which ultimately means the reaction doesn't have a direction it favors. So while adding sodium hydroxide to an alcohol does remove a hydrogen, it doesn't remove it in a very high efficiency. Okay, and that's why we end up with an equilibrium reaction. So that species, our product, can just as easily share its electrons with water to go back the other direction. Okay, so if we're trying to decide on what reagents to use to make a reaction go forward, go where we want it to go, we want to try and minimize these equilibrium reactions as much as possible. We want it to favor only our products, because if it favors somewhere in between, we don't get a result, okay, or we don't get as much of a result in as little time as possible. Remember, think back to lab. You want to get out as fast as possible, okay, within safety reasons. Okay, when we go through and evaluate sodium hydride, well, what's the big difference? Okay, well, now when we compare, okay, since I showed the sodium there, let's go ahead and get rid of that. We've got hydride floating around. So when we go and evaluate, in this case, our most reactive species, we're going to say hydride again because of that negative charge. And we can move over to our products, and we would say the ethoxide, our oxygen being negatively charged. So those are reactive things. And now if we try and decide which side is better, okay, well, where would I rather have electrons? On an oxygen atom or a hydrogen atom? Well, what's the difference between hydrogen and oxygen? First thing we do is look at size. Oxygen's bigger. That's already something favoring oxygen being negative. And then we could also look at electronegativity. Oxygen's also more electronegative than hydrogen. Okay, so really what we're saying is that this species, our product species, is a lot more stable than our products that is ridiculously unstable. Okay, which means our reaction pushes only one direction. We only go towards our products. We don't get an equilibrium reaction. We favor just that products. So we can now make our nucleophile. Okay, so that's something that we would want to consider when running a reaction. Okay, as far as testing on this, I haven't decided strictly how many points I would weight towards specifying hydride versus hydroxide. I'll probably will give equal points for either in an individual reaction because you're getting at the right idea. You're still trying to use a strong base to remove that. Nailing down the specific reagent necessary to make that transition, I tend to hold a little bit of wiggle room on. Okay, because you guys have cheat sheets, you should have written down on your cheat sheet to deprotonate an alcohol, you should be using sodium hydride, not hydroxide. Okay, so that if you see that reaction where we're transitioning and I ask you for, fill in the box, you should be writing hydride, okay, because you should have that notes or have that reaction in your notes saying, hey, alcohols to form nucleophiles need to react with hydride. Kind of makes sense? Okay. Another thing that we can do to kind of evaluate why this reaction might be helpful is in our first reaction there, that equilibrium one, you notice that I used those orange arrows to say that the ethoxide could react with the water to pick up another hydrogen. Well, let's go back and see what we can do in the case of our second reaction. As I'm calling first and second, let's go ahead and number them. Okay, well, how about that negative react with one of those hydrogen ions, or a hydrogen atom in H2? Well, how likely is that? Number one, we're looking at a nonpolar bond, nonpolar covalent bond. So neither of those hydrogens is particularly positive, which reduces their reactivity. Okay, so that's not a particularly likely thing to occur. What else is an issue? Well, what's the phase? When I run this reaction, I actually remove that hydrogen altogether from the reaction as a gas. So now when I form this ethoxide, our negatively charged alcohol, it can't go backwards. There is no hydrogen for it to react with to go back to the starting material. Okay, so multiple reasons why we really want to be using a different base than sodium hydroxide. Okay, so we're just trying to, again, maximize the yield as far as our reaction goes. Okay, hopefully that kind of makes sense. And before we completely kind of ditch this concept, I'm going to address one more quick thing with this. So I'm going to erase a lot of this. So when we go through and look at the hydride, or even with our negatively charged oxygen, one of the things we're driving for is making it a really good nucleophile. So in both these cases we've got a good nucleophile. And as we've seen in other reactions, if we have a good nucleophile, we typically also have a good base. And that's because our nucleophile and bases both are negatively charged. Okay, so let's go back and evaluate our hydride. Okay, we've got H minus. Okay, well, if it's H minus, that means it could act as both a nucleophile and as a base. Okay, and bear with me, this is a bit of a tricky subject here. So the difference largely between our base and our nucleophile was ultimately one of size. The smaller it was, typically, the more we said it was a nucleophile instead of a base, because it could get in and react with the electrophilic atoms. So when we add sodium hydride to an alcohol, we might expect it to act as a nucleophile. And it turns out that that reaction does not occur. Okay, so the hydride is actually kind of neat in this respect because it only acts as a base. It doesn't act as a nucleophile. Whereas if we go up and take a look at our hydroxide up here, this can act as a base and as a nucleophile. So it could get in the way if we had some other functionality in our reaction. So the hydride's kind of neat for this reason. Okay, but that seems very counterintuitive to all the rules we've discussed so far. Our nucleophile should be small. Hydride is small. It should be a good nucleophile, and it's not. Okay, and this is kind of a trickier aspect. I would kind of only expect maybe 10-20% of you guys to kind of walk with me on this little journey here. Sodium hydride, and in particular that hydride, is so ridiculously unstable that bond is kind of maintained, and sodium hydride remains as a solid. Okay, well, why is that important? Well, for our hydride to act as a nucleophile, it must be free-floating in solution so that it can get close enough to do that backside attack. Okay, well, if it stays as a solid, we get very minimal interaction between our alcohol and our hydride species. Okay, so because it's in a different phase, we're ultimately looking at very minimal contact. The only thing it can really come in contact with is the hydrogen atoms on the outside, okay, or our acidic hydrogen atoms. Okay, so it's kind of a tricky situation there. It's one that I wanted to address in case somebody saw that there was a problem with that. Okay, so hydride will only act as a base. It's a terrible nucleophile in this case because of this pseudosteric effect, okay, even though it appears to be small. Okay. With that said, let's go ahead and advance to another possibility here. You'll notice I'm adding one more thing. So instead of now just having sodium hydride, which is our, go-to base, you might also see the addition of, whoa, slippery pen. You might also see the addition of sodium metal. So this isn't sodium ion, this is sodium solid. Go on YouTube, sometimes you'll find these videos of sodium blocks being dropped in water. You'll see them get launched out and all these fancy funny things happen with them. Okay. And what's ultimately happening is sodium metals and anything underneath them will react with water in an acid-base reaction. Okay. And in the process, that reaction is so violent and it releases hydrogen gas to such a large extent that they end up launching these sodium bricks out of the water, okay, because there's so much pressure being pushed on that species. Okay, so if we add sodium metal to an alcohol, we get a very similar reaction because of that acidic hydrogen. Okay, so what ends up happening is sodium metal, it has 2 electrons. It can donate those to hydrogen. The electrons in that bond then go to oxygen, and as an intermediate, we generate, first off, our negatively charged oxygen. Oh man, too small, I can't quite draw it. So we get our negatively charged, can't draw it right today. Try that again. Negatively charged oxygen, and we would get sodium hydride. Well, now that we have sodium hydride, it can react again with another alcohol. React again with another alcohol to deprotonate yet another one, and so what we end up getting is that sodium metal will react with 2 alcohols. So this is for those of you that like to balance things. So if we ran this reaction, sodium metal with 2 alcohols will produce 2 deprotonated alcohols, or 2 oxides, sodium ion and hydrogen gas. Okay, I just want you to be aware of that extra version of it. Sodium hydride is merely one step after sodium metal reacting with an alcohol or reacting with anything acidic. Okay, so just another reagent to use. Okay, so the next part of this, hopefully, because I've now forgotten, is crap. So before we get into the eliminations, let's take a look at an example. So, is doing something. Let me pause. Okay, I know that was a pretty sudden transition there. I don't know quite what went wrong, but I wanted to do is go back to this quick reaction here, and let's go through and look at a mechanism for it. Okay, so let's draw that out in our larger whiteboard pattern so we can make sure we can see what's going on with that. So we're going to start with our alcohol. And I don't know if I'm drawing the exact alcohol. It doesn't need to be exact. With our hydrogen, we said step 1 was to react with sodium hydride. Okay, so if we want to be super strict with this, remember I said this was a solid. So what's going to happen is that our electrons from our sodium hydrogen bond will react with our hydrogen atom on our alcohol. Those electrons go to the oxygen. Okay. The result is that we get our oxygen now with an extra pair of electrons, which I'll go ahead and show in blue, and we would get our sodium ion and hydrogen gas. So this would all be step 1 of our reaction. If we then move to step 2, so now that we've done this initial reaction, we say, okay, now I've got my active nucleophile. Okay, so our alcohol is now a really good nucleophile. Okay, so a strong one. We could then react it with, I think I did ethyl bromide. Okay, so when we go ahead and take a look at ethyl bromide, that's a bit interesting because the bromine has all those nice little electrons, is partially negative because it's electronegative, which means it's taking electrons away from our carbon, so our carbon is partially positive, so we now have an electrophile. So our electrons from our nucleophile can come in and attack. I should do that in blue because I've been showing those other arrows. Can attack the carbon, sharing the electrons with the carbon, make it a little bit happier, and then we'd have to break the bond between our carbon and bromine, and what we end up with as a final result, oxygen, and then our bromine. There's our lone pairs on our oxygen, and if we want to get extra fancy here, there's our new bond. Okay? So it's ultimately the same types of reactions you've been seeing before, except what we've done is added an extra little step. Okay, and that new step is step 1. What type of reaction occurred there? Good. Hopefully you can see that what we did was a hydrogen transfer, so we're looking at an acid-base reaction. Okay, and in this case our alcohol acts as the acid to make a good nucleophile. Once we have the nucleophile, we can move to step 2 and perform a substitution reaction. Okay, so let's push it even further. What type of substitution reaction did we do here? Okay, strong nucleophile, primary alkyl halide, or primary substrate. We're looking at an SN2 mechanism. Okay, so I just wanted to make sure you saw that extra step. So there's 2 ways that we can really approach our alcohols. We can have them react as nucleophiles, or have them act as acids first, so that they can then be a nucleophile, or what we can do if we push back all the way to our initial substitutions, we can have them act as bases so that the carbon acts as an electrophile. Okay, because in each of these cases, our carbon here was what picked up the new atom, so that's where our chemistry occurred. Okay, so we can either have our alcohol act as an acid first and then become a nucleophile, or we have it act as a base and make our carbon act as the electrophile. Okay, and that's so we can get both directions for our substitution reactions. Okay, so the last thing I want to cover here before I go ahead and call it quits, sorry, we're going to move through some of these slides fast because we saw those, is looking at our elimination reactions. So you need to be familiar with the E2 and E1s and remember what's happening with these. As overall thoughts, just as kind of little addendums we can add on here, E stands for elimination. So if you looked at an overall reaction, what would you expect to be the result of an elimination? So we could say our reactants go to our products, and our products would equal the new functional group of an alkene. Come on. Of an alkene. Okay? So the things that control those, similar to the same ideas as your substitutions, you should have these or this chart memorized so that you're familiar with what products come out of it. Okay? One of the big things that's going to change here between our substitution elimination mechanisms is that our E2 favors tertiary and then reduces down to our primary. Okay, and that's ultimately because we want a stable product, and that really comes in with Zaitsev's rule. Okay, so if that terminology threw you for a loop, go back, review the elimination material from chapter 7, and make sure you're comfortable with what's happening there. Okay, so what we're going to go ahead and do is walk through one example with our alcohols, and then we will call this lecture quits. And pick up on Monday with our oxidation reactions. So, elimination reactions. So if we're going to take a guess at a product here, we need a new double bond. So we could try and evaluate the reactivity. Let's just do a new double bond. So if we were going to draw this out, more than likely we're going to form a double bond around our most reactive carbon. So that carbon's going to be our most reactive. I can't form a double bond this direction because then I wouldn't be an alkene. Okay, I'd be looking at a carbonyl, and we haven't seen that reaction yet, so we'll pretend that we don't know it, which means we have to form the double bond, the other direction. So as an answer, we would expect that our double bond forms out here, and we would get a butene. Okay, so how does this actually occur? Okay, so let's ignore that arrow. So let's go back to the starting materials and say, what chemistry do we see here? And we can pull my ever so popular face test, alcohol versus H+. Which would you rather have splashed in your face? Hopefully you would say the alcohol. So that means the acid is our most reactive one. Okay, the other thing we could do is just look for charges. H+ is charged, the alcohol is not. More than likely H+ is where we should be focusing our attention. We need to stabilize that positive charge as best we can. Okay, so how can we stabilize it? What does that positive charge need to neutralize? Okay, electrons. Where do we have electrons? Okay, well, the oxygen's got electrons. So we can have the lone pair on the oxygen share with that hydrogen. Okay, so let's draw that out. What does that end up looking like? Okay, we didn't touch one of those double bonds, so we'll leave that alone. The other one we adjusted. Okay, so we could go through and calculate formal charge, or we could evaluate that our starting alcohol started neutral and shared electrons, so it is now positively charged. Okay, so very similar to the reactions that we just looked at, or we looked at on Wednesday. Okay, what type of reaction is this? We're looking at an acid-base reaction. The alcohol acted as a Bronsted-Lowry base, and of course H+ acted as our Bronsted-Lowry acid. Okay. So now that we've got this new species, we'd say, okay, now we've got to evaluate its stability. Okay, well, oxygen doesn't want to be positive, so we'd try and find something negative floating around. Okay, so one of the things that you should note here is if we go all the way back to our starting material, you'll notice that I don't provide a conjugate negative species to stabilize that positive. And there's a very good reason why I didn't do that. And we'll look at that in just a little bit here. We'll look at it right now. If I have a negatively charged species floating around, that can potentially act as a nucleophile and do a substitution reaction. Well, is this a substitution reaction? I don't know, you tell me. What are we focusing our chemistry on here? This is supposed to be an elimination. So we don't want to be looking at a nucleophile. Okay, so we'll erase that and say we don't have a source of electrons outside the structure. Well, if there's no electrons outside the structure, where do I have to look for electrons to stabilize that positive? All right, we're going to have to look within the structure. Okay, so oxygen is going to try and steal electrons from someplace. It really only has two options, hydrogen or carbon. Either hydrogens are equivalent, so we don't really care about those. If we did pull off the hydrogen, we would just be going backwards. Okay, so we'll add that. Hopefully no one can see this. I'll add it as a yellow color. Yellow would take us backwards, so that's bad. Okay, so we don't want to evaluate that one. Let's see if we've got something else. Okay, so we could try and take the electrons away from the carbon. Okay, and when I've been teaching this before, I didn't draw out products because I didn't want you to draw this out, but we're going to go ahead and adjust because a lot of you guys have been skipping or just drawing it out, so we might as well stick with that. Okay, what's the result? We still have 4 carbons. We generate a positive charge on that carbon because it's now lost electrons, and then we've got our oxygen atom, which picked up 2 more electrons. So the oxygen becomes neutral, great, but now our carbon's positive. Deciding or evaluating between those two, which is better, a positive oxygen or a positive carbon. Positive carbon because it's less electronegative than oxygen. So all in all, that doesn't seem too bad, but we do run into an issue here. What's that issue? This carbon is only bound to one other carbon, so it is a primary carbocation. Okay, that's a bit of a problem because we said our primary carbocations are so unstable they don't form, which means the mechanism that we've drawn, our red arrows back here, aren't enough. I cannot progress forwards, so what I'm going to have to do is now bust out the eraser and erase all of this stuff. Okay, and I have to somehow fix that. I do know that that carbon is becoming partially positive, so that is something that is helpful, but it can't be formally positive. Okay, so if that carbon becomes partially positive, I need to get electrons to it to permanently stabilize it. Okay, and I'm going to have to do that before oxygen takes the electrons. Okay, or as oxygen takes the electrons. Okay, so now what we have to do is evaluate where else in the structure do we have electrons. Okay, well, as it's drawn, we could see bonds. Okay, so we could try and pull from this bond. That ends up breaking it, so everybody hates this, but we're going to end up doing this a whole bunch. We're going to draw and erase a whole bunch here. So we could draw this out. That bond's no longer there, so I now have just that carbon chilling on its own. The oxygen kicked off and was neutral. And then we'd have, oh man, we'd have a CH2 with a lone pair of electrons. Then what happens to this carbon? Well, it just lost electrons, so it's positive. So now we get a lot of pieces, and it's probably worse off than before because we haven't even evaluated that species to decide if it's even remotely stable. Never mind the fact that we've got a primary carbocation, and the primary carbocation was what we said we couldn't do to begin with. So getting the electrons from there, still not a good option. So let's try again. Okay, we could try and take our electrons from, say, here. Okay, oh, well, that's a little bit better. And the result of that, what do I get? Well, I would have these 2 carbons, but now I've got a double bond there. OH2 came off. Good, we've got the elimination, but that arrow means that our carbon, this carbon in particular, lost electrons, so it's now positively charged. Ouch. We're getting closer because we're now forming the double bond and we're getting our elimination reaction, but we're still making something ridiculously unstable, that primary carbocation. So yet again, doesn't work. Okay, so now we're kind of at a loss because we can't pull electrons from any further away. So something's got to be missing. So what are we forgetting about? Okay, hopefully you can remember we have implied hydrogens on that carbon. So what we can do is take the electrons from those implied hydrogens and shift them into a bond. Okay, so we'd be making a pi bond. Okay, so if we drew this out, what's the result of this reaction? We didn't touch our other carbons, so we'll draw those on. We now have the double bond here, have our hydrogen here, and we would have OH2, a nice little lone pair. Okay, so what happened to our partially positive carbon? Okay, so let's go ahead and flag that as blue. Okay, well, the first thing that happened was it lost electrons to the oxygen, so it becomes positive. But then it gains electrons from our other hydrogen, which I forgot to draw on here, so let me add that real quickly. It gains electrons from our hydrogen, so loss and gain, we end up right where we started, which was neutral in this case. Okay, so seems reasonable. The next thing we've got to evaluate here is what makes this unstable. We've got H+. Okay, well, H+ floating around, we had that floating around to begin with, and we said we didn't particularly like that. But in the process of this reaction, we have sort of stabilized it. We made a reactive species, and now we made a less reactive species. Okay, so we changed the reactivity. And if we now compare what we decided was our final product, our final organic product, to what we guessed was our final product, oh, wow, those look awfully similar. In fact, I would say the only difference between these was that I didn't draw the hydrogen. Okay, that hydrogen ended up being implied. Okay, so when we go through and do our elimination reactions, they will still require that acid-base initiation, okay, to get the alcohol active enough to react. After that, we can start to move through our elimination mechanism. Okay, so we really just went through two steps here. We had our acid base, and then we had our second step over here, which was which type of reaction? That was our elimination. Which mechanism? We've got an E2 mechanism because we said it all happened at once. Why did it all happen at once? Because we had a primary substrate, okay, or a primary alcohol. That alcohol forces the two-type mechanism. Okay, we don't have a choice. Okay. Are there other conditions under which we could do this reaction? So, number one, we had to make sure that we didn't have a nucleophile. So that was really, really important. We had no nucleophile in this reaction, so that was something we needed. One of the other big things that I told you guys to watch out for with our eliminations is that we'll likely also see heat added to the reaction. I didn't show it in this case, that was a bit mean of me. Okay, heat or maybe even a delta symbol. Okay, so that kind of summarizes everything with the eliminations, except there's one more aspect we can evaluate. We said our alcohols can act as both acids and as bases. Okay, well in this case, our alcohol acted as an acid. Could we have instead reacted this with a base? After all, when we get to our elimination step, what's going to pull off the hydrogen? Okay, well we need a base. Okay, with some lone pairs. So let's go through this whole reaction, but instead of adding H+, we add OH-. Okay, well now what's our reactive species? OH-, so we need a positive. Where's there a positive? Okay, well we've got a positive on that hydrogen and a positive on that carbon. If you go back and take a look at your notes for that last one, we had to remove a hydrogen from that next atom over. Is that hydrogen partially positive? I'm sensing some yeses because we said that it had to have been positive for the previous reaction to work. Okay, so let's kind of work with that. Let's say it is positive for sake of argument. Okay, when we're going to run a reaction, we're going to take our most negative and our most positive. Those two are going to be what's going to react. So we can say this hydrogen's positive for the moment. So now let's evaluate. Which of these is the most positive? Okay, well, let's start with, I'm not going to make it color-coded, our blue hydrogen. Okay, well, that's attached to an electronegative element. Electronegative, that's going to be a partially positive carbon, or hydrogen, sorry. Okay, so that's pretty reasonable. Okay, and for effect, let's go ahead and make it a little bit bigger. We'll see why in a second. Let's move left to or right to left. Now let's take a look at our carbon. Okay, well, that's going to be partially positive too because it's attached to an electronegative element. Is it as big a partial positive as with the hydrogen? Okay, well, what's the difference? It's still the same oxygen drawing electron density away, so we have to evaluate hydrogen to carbon. What's the difference between hydrogen and carbon? There isn't much, but carbon is slightly more electronegative, which means it's holding on to the electrons in that oxygen-carbon bond ever so slightly a little bit tighter, which means our partial positive isn't quite so big. Okay? What happens with our very last hydrogen? So now we'll go call it our red hydrogen. How partial positive is that hydrogen? Okay, well, it's attached to a carbon. What's the difference in electronegativity there? Not much at all. So it's probably partially positive, but of our choices, it's probably the smallest. So now when I go through and try and decide what's going to occur in this reaction, well, I'm going to take my most negative, which in this case is the hydroxide, because it's negatively charged, and react it with the most positive, which in this case is my blue hydrogen. Shuttles the electrons to the oxygen. What do we get as a result? Okay. Does oxygen want to be negative? No, so it's going to want to find a positive. At best, what we might see, because we've actually even looked at this reaction, and we've got water. So does oxygen want to be negative? No, so it's going to find the most positive. Where's the most positive? On our hydrogen there, and we get the reverse reaction. Okay, so we go right back to where we started with. So interesting. We add a base to our alcohol, we don't get the elimination reaction. Okay? Our elimination reactions require that we have a leaving group. Okay, so in the case of this reaction, we need this OH to act as a leaving group. Okay? Our alcohol must leave. For it to leave, it must be stable. Okay? If it leaves as OH minus, we generate a strong base, highly reactive, not very productive. And we would expect the reverse reaction. Okay? So we must, for elimination reactions, okay, because I don't think I've got this on a slide, I'll have to write it out. For elimination reactions, alcohols must act as a base first, okay, which means that they become H2O plus, which is a good leaving group, and then we can eliminate. Okay, so the first step for all elimination reactions will be, or alcohol elimination reactions will be adding H plus, followed by anything else that we want to do. Maybe we can even do, say it's step 2 as heat. Okay, we must activate the alcohol for elimination, so we have to have it react with an acid. Okay. I think that's it. I mean, only 50 minutes later, but be prepared to go through the rest of the slides on Monday. I will have another quiz ready for you, and I will try and get that posted hopefully within the next 2 hours as well, so that you can find on Canvas. If you've got any questions, write them down so that you can ask, slow me down on Monday to ask those questions, or you can slow me down on Wednesday, which will ultimately be a much larger review day. Okay, I hope you enjoy the rest of your weekend, and I will see you Monday.